Okay, that was a short minute, but all of a sudden my clock reads 9:30. So let's go ahead and get started this morning. And today we are making the jump into hypothesis testing. So in this discussion, I'd actually like to start by kind of reviewing where we've already been in terms of the research process. So at the beginning, we learned how to ask good questions that could form the basis of a study and then form our hypotheses, our predictions that would really lay out how to conduct that undertaking. We talked about operationalizing our variables, making sure our measurements are both reliable and valid. We also talked about how it is that we might design our various research studies, of course, taking ethics into account. And along the way, we do need to collect our data, and you did that in your labs. Hopefully we have a representative sample, although at times we must use a convenient sample, of course, which is going to be non-representative. And then for the last couple of weeks, we've been focused on how it is we summarize our data. And that is where descriptive statistics come into play. So that's where we are at the moment, and we're going to be pushing forward. So let's think about what comes next. We've described our data. That is, we've described what the data look like in the sample. But we want to make conclusions not just about this subset of individuals that we've examined, but about the broader population from which those subjects are drawn. We want to make our conclusions about that population. So we need a way to determine whether patterns in our sample data are real, whether they reflect something about that population, or it's just something about the sample we have, just some random noise, some sampling error. That is where inferential statistics come into play. So inferential statistics are techniques that allow us to make conclusions about that population, even though what we've collected is a limited set of sample data. We're making inferences, hence the name inferential statistics. So we're going from that sample to the population and using statistical techniques to determine what conclusions can we reasonably make. So in inferential statistics, the big picture question we're asking is basically, do we have enough evidence? Do we have enough evidence to make a conclusion that some sort of pattern we think we're seeing in our sample actually exists in the broader population? If we were to actually examine every single person who might be relevant to the question we're asking, would this pattern that we're seeing actually hold up? I want to start today with a little story, an example of inferential statistics at play. In fact, it's perhaps the original example. I'm going to give you a brief retelling of this story, but I have posted the full story to your class page under supplementary readings, and I would encourage you to read this through. So Ronald Fisher was a British mathematician in the 1920s. And he had been hired by a research institute to help the scientists design better studies, better experiments. And he was kind of at a loss. He wasn't really getting too far. Well, one day he was taking a break. This is Great Britain as well. So he was having afternoon tea with some friends, some colleagues. And one of the colleagues there was a woman named Muriel Bristol. She was actually a biologist. So at the time, a female scientist, relatively rare, but anyways, he was having tea with her and another colleague named William Roach. And he knew that Muriel took her tea with milk. So he poured some milk into a cup and he poured the tea on top and he gave her tea and she said, yeah, no thanks. Now I'm sure she said it in a very dainty and British way, but she refused the tea. And she stated that she only drank tea when the milk was poured in after the tea. And she insisted that it tasted different if the milk was poured in first versus after. Now, Ronald Fisher thought this was completely ridiculous, and he told her so. I mean, if you have the same amount of tea and the same amount of milk and you mix them together, how could it possibly matter which goes in first? But she insisted they tasted different and that she could tell. Now, it turns out that scientifically she was actually right, although it wasn't known at the time. There's a chemical reaction that occurs when milk droplets hit very hot liquid, and that can only happen if the tea's there first and the milk starts to splash in. But that wasn't known, and that's kind of beside the point. So Fisher and Bristol, they're arguing, and then William Roche steps in and he says, let's test this. Let's do a little experiment. So the study they devised, they went to the back and they created 8 cups of tea. Each was poured from the same teapot and had the identical amount of tea and the identical amount of milk. But in 4 of those cups, the tea was poured first and then the milk on top. And in the other 4 cups, the milk was poured first and then the tea was poured on top of it. So milk first or tea first. And then they mixed up the cups. They kept track of which was which, but they put them in a random order and they presented them to Muriel Bristol, and she was supposed to taste each cup of tea and indicate whether the tea went in first or the milk went in first. And Ronald Fisher is convinced that she's going to get, at least half of them wrong, because it's chance. Well, she sips the first cup of tea and she confidently says, milk first. And she was right. And she sips the second cup of tea and she confidently says, milk first. And she was right again. And she sips the third cup of tea and she says, that one's tea first. And she was correct. And she went through all 8 cups of tea, each time declaring with perfect accuracy whether it was tea first or milk first. And of course, Ronald Fisher, who's having to eat his words, is just getting more and more dumbfounded by the moment because she could clearly tell the difference between these various cups of tea. And later on, he calculated the he knew it was a very unlikely scenario that she would correctly get all 8 cups correct if she really couldn't tell the difference. But later on, he calculated that probability. It's 1 in 70, or about 1.43%. If she really couldn't taste the difference and was guessing, she would only get them all right 1.4% of the time. But she did it. Now, Ronald Fisher had this brewing in his mind, no pun intended, for a while, and realized that this way of thinking could form the basis of doing better experiments, better research. And this is actually kind of the birth of modern statistics, what they did with Muriel Bristol. They started from a place of skepticism, not believing that anything possibly could be going on here, convinced that they were going to find random chance in her guesses on the tea. But they set up a study and they examined the data. And when the data emerged, that was very unlikely to occur if it was purely random chance, they rejected that place of skepticism, what we're going to see we now call the null hypothesis. And well, if that's wrong, then the only other possible explanation is that there is a difference, that we do have an effect here. And so this idea of starting from a place of skepticism and looking for data that we really would be unlikely to see if there's nothing going on, that is the way that we now do our statistics. And that is a brief version of this story about the lady drinking tea. There's a question in the chat. Let's be real, the pun was intended. Well, maybe. It was halfway out of my mouth when I realized what I was saying. Let's go on and talk about how we do this. So, the idea I'm going to introduce now is the notions of the null hypothesis versus the alternative hypothesis. So when we do our statistics, we set up two complementary types of hypothesis statements. And what I mean here by complementary is that one or the other must be true. They are directly opposite one another. So if one is false, the other one must be true. There is no way around it. They cover all possibilities. So it's one or the other. So the null hypothesis, which we use H naught, H with that little sub-zero, we call it H naught to symbolize. This is the hypothesis that we're actually going to test with our statistics. It's the hypothesis that represents that place of skepticism. Yeah, nothing's going on here. The alternative hypothesis, as I said, it's complementary. It's the opposite of the null hypothesis. So if the null hypothesis is false, then the alternative hypothesis must be true. It's one or the other. Now, typically, the alternative hypothesis maps onto your research hypothesis. It's what you predict will actually occur in a study. So Muriel Bristol in the T study, she would be the one with the alternative hypothesis. I can tell the difference. I'm going to get every single cup correct, or at least many of them. Okay. So again, they're set up in a complementary manner. So one or the other must be true. To give you a completely ridiculous example, I frequently ask the question in my household, where have all the socks gone? Usually it's my kids' socks. And they would love for me to believe that it was aliens that stole all the socks. That's their alternative hypothesis. It's aliens. I'm a little skeptical. There are many things that might have happened to those socks, many, many things, some of which I really don't want to even think about, but probably not aliens. One or the other must be true. Either it is aliens or it isn't. No other possibilities. Okay, we're going to look at some more realistic examples in a moment. But before we look at the more realistic examples, I want to sort of look at the big picture. So we have a null hypothesis, which we abbreviate H naught, and then the alternative hypothesis, which traditionally we would use H sub 1. Sometimes you'll see this abbreviated as H sub A, but we'll use H1 here. Now, our hypotheses can be non-directional or directional. So a non-directional null hypothesis, remember the null hypothesis, nothing's going on here. No effect, no difference. Two groups are similar, or if we're doing a correlation, one thing is not related to the other thing. The alternative hypothesis then is that there is an effect. There is a difference. Two things are dissimilar. Or if it's a correlation, two things are related to one another. Notice that there's no direction being predicted here. It's a non-directional hypothesis. Two groups are different from one another in that alternative, not one is greater than the other or one is less than the other. For our correlation, we're saying for the alternative that two things are related. We're not saying that they're positively related or negatively related. We're actually not predicting a direction here, just that there is versus is not a relationship. So those are all non-directional hypotheses. The null hypothesis predicts that there is nothing whatsoever going on, and the alternative hypothesis says that there is something interesting to see. Now, other times our hypotheses are in fact directional. So in lab, you have been encouraged to make a directional hypothesis about your correlation. As sleep goes up, happiness goes up, or whatever the case may be for your variables. Or as the level of sleep goes up, stress level goes down. Okay, so it's correlational and it's got a direction. So our alternative hypothesis is the one that maps onto what we believe is going to happen in our experiment. So we might say that one thing is larger than the other or is smaller than the other. Or we might say that there is a positive correlation, a positive relationship between two things, or a negative relationship. The null hypothesis is not larger if we're predicting that it is larger, or not smaller if we're predicting that it is smaller. It's the opposite. So let's look at some concrete examples here. So I have a table in your notes, and we're going to work through them one by one. For each example, we want to figure out if the hypothesis that's being given is directional or non-directional, and if I've given you the null hypothesis or the alternative hypothesis. And then we'll figure out what is the other one. If I've given you the alternative, we'll figure out the null. If I've given you the null, we'll figure out the alternative. So let's get started here. So the first one, age is a significant predictor of income. What do you think here? Is this directional or non-directional? Let's start with that. Am I predicting a specific direction here? Julia, it looks like you've unmuted yourself.
Non-directional.
Good. This is non-directional. Thank you, Julia. I'm not predicting that income goes up as age goes up or income goes down as age goes up. I'm just saying that there's a relationship. One predicts the other. So this is non-directional. Now, is this a null or an alternative hypothesis? Shelby? I heard something there, but not quite an answer.
This is a null hypothesis.
It is what, I'm sorry?
No.
Why is it a null hypothesis?
Because you can use like income as like a statistic, and you can find out with age as well with that.
So you absolutely can use statistics on income and on age. You're right about that. But that's not what's going to define this as a null versus an alternative hypothesis. So we really want to look at what is being predicted. Are we predicting no effect, or are we predicting that there is an effect? Here we're predicting that there is an effect. So that means that this is an alternative hypothesis. If we say that age is a significant predictor of income, we're not being skeptical here. We think that there is something going on, that age and income are related. So that actually would be an alternative hypothesis. The null hypothesis then that pairs with this, what would we say?
Age is not a significant predictor of income.
Thank you, Sarah. The null hypothesis, the H naught, is that age is not a significant predictor of income. There's no relationship. There's nothing going on. You've completely wasted your time by doing this study. Nothing interesting to see here. That's the null hypothesis. Let's do a second one. Gay males and heterosexual males have similar mental health scores. Is this directional or non-directional?
Non-directional.
Thank you, Sarah. This is non-directional. We're not saying that gay males have higher mental health scores. We're not saying that gay males have lower mental health scores. There's no direction predicted here, just that they are similar. So it's non-directional. And is this a null hypothesis or an alternative hypothesis?
It's an alternative hypothesis.
It's an alternative hypothesis, says Rachel. Why?
Because it is predicting that there is some kind of relationship. It's not saying that it has no effect or anything like that.
It's not saying that there's no effect. You're looking at the right information, whether or not it's predicting an effect or not an effect. But the word similar kind of means that there isn't anything interesting going on. So this actually is a way of predicting no effect. So this one's actually a null hypothesis, that they are similar, that they look pretty much the same. Again, nothing interesting going on here. Does that make sense? So I'm going to ask Rachel again, if this was an alternative hypothesis, now that you see it, how might we phrase it? What would the alternative hypothesis that goes along with this be?
Maybe it could say something like gay males and heterosexual males. I don't know. Mental health scores are.
You're almost there.
I don't know. I'm trying to like word it. Like, let me see here. So
I'll give you a hint. You only have to change one word here to make it work. So instead of similar, it would be
like related to, or like I don't know,
okay.
like
I think the problem here is that you're still thinking about correlation. And it makes sense that you're thinking about correlational hypotheses because you've been working on correlational studies. But remember that not all predictions we make are going to be about relationships, about correlations. Here we're just comparing two groups, maybe the mean mental health score of one group versus a different one. So we're not trying to see a relationship here. We're comparing the means of two groups. So somebody else, you want to jump in here and see if you can phrase an alternative hypothesis? Or Rachel, if you want to take another crack at it, anybody can go here.
Gay males and heterosexual males have different mental health scores.
Good. Gay males and heterosexual males have different mental health scores, or you could also say dissimilar. Either they're the same or they're different. One of those two things must be true. How are those feeling so far? Okay, not hearing any massive objections, here's what I'm going to do. I am going to put you guys into breakout rooms. What I would like you to do is work through the other 4 examples. Again, for each, figure out non-directional versus directional, and whether the one you're seeing is the null or the alternative, and then figure out what the other statement, the other hypothesis statement would be. So take a few minutes in those rooms and let's see how far we can get. Here we go. Go ahead and join your rooms. We'll just wait for everybody to rejoin our room. Let's give it another minute or so. 30 seconds. So how do you feel like those went? I'm seeing a couple of thumbs up and a few faces that tell me maybe not. We are going to discuss each of the examples. So let's get started with that. So here is the first one that you were working on. So let me ask you first what y'all came up with. Children are more creative than adults. Is that a directional null hypothesis, a directional alternative hypothesis, a non-directional null hypothesis, or a non-directional alternative hypothesis? Going to give folks a moment to shift gears and get back into the room and with their wreath on. If you have not already responded, please do so within the next 10 seconds or so. Okay, I'm gonna go ahead and stop it there. Let's see what we have. Okay, the most popular answer, as you can see, hopefully it popped up on your screen, is directional alternative. That answer is in fact correct. What word tells us that it is directional?
More.
More. So we're not just saying that things are different. Children are more creative. So that is directional. And why is this an alternative hypothesis and not a null hypothesis?
Because it says they are instead of like they're not, or children and adults are the same amount of creative. Or...
We're saying that they are more creative. It's a kind of a positive statement. So this is an alternative hypothesis. Good. What would the null hypothesis that goes along with this be?
I said children are just as creative as adults.
Children are just as creative. So basically that they're the same. Now remember that we need to cover all of our bases. So they're opposites, they're complementary. Everything has to be accounted for, so it's one or the other. So children are more creative, children are equally creative, just as creative. There's another possibility here though, and that is that children are less creative. So that doesn't quite cover all of our bases. So what would the null hypothesis be?
Could you just say children are not as creative as adults?
Children are not more creative than adults. That would be what we would want to say. Children are not more creative than adults. Either they are more creative or they're not more creative. Now notice here that just as I didn't say that they're just as creative, they're equally creative, I also didn't say that they're less creative, because that would leave out the possibility that they're equal. So either it's more or it's not more, meaning same or less. And that covers all of our bases. And that's a really important thing to do here for reasons we're going to see. Okay, let's do the next one. Psychologists have lower mental health scores than the general population. What is this one? I'm not going to leave this as open for quite as long, so ring in your response. About 10 more seconds. Okay, I'm going to stop it there. So please do ring in if you have not already and you are able to. Okay, let's see what we have. Once again, the most popular response here was directional alternative. Once again, that is the correct answer. Some of you might have been fooled thinking she wouldn't put two the same back to back. Oh, but she would. This is also a directional alternative hypothesis. We know it's directional because it is lower, not just different, but lower. And it's an alternative because we're making a specific prediction. Psychologists have lower mental health scores than the general population. Can somebody apply what we did in the last example and tell us what the alternative hypothesis here would be?
The psychologists do not have lower mental health.
Thank you, Tyler. Yeah, psychologists do not have lower mental health scores than the general population. Exactly. We're covering all our bases. Either they're lower or they're not lower, meaning that they're the same or higher. There you go. Okay, next one. Boys and girls have a different number of imaginary friends. What is this one? Five seconds to ring in. Okay, let's take a look and see what we have here. Now our most popular answer is still alternative, but non-directional alternative. Correct. Good. It's non-directional here because we're not saying that boys have more imaginary friends or that boys have less imaginary friends. They're just different from the girls. So that's a non-directional prediction. And we know it's alternative because we're not being skeptical. We're not saying there's nothing interesting to see here. We're making a prediction that there is something interesting going on. So that's an alternative hypothesis. Boys and girls have a different number of imaginary friends. What would be the null hypothesis that would complement this?
Boys and girls do not have a different number of imaginary friends.
Good, thank you, Lauren. Boys and girls do not have a different number of imaginary friends. Or if we're lazy and we don't want to write that many words, we could also say that boys and girls have a similar or the same number of imaginary friends. Yours is fine, Lauren. It's just more words. And I used the similar version. So they're similar or they're the same. Good. Okay, how are we doing with that one? All good? Okay, then there's just one more to take a look at. Females do not earn lower salaries than males. Yeah, right. Ten seconds to ring in. Okay, let me stop it there. Yes, indeed. This is a directional null hypothesis. We're saying that they do not, so it's null, earn lower salaries. The lower there tells us directional. What would the alternative hypothesis be for this case?
Females earn lower salaries than males.
Thank you, Skylar. Exactly. Females earn lower salaries than males. Either they do not or they do. One of those two things has to be true. So those hypotheses are perfectly complementary. Okay, this got better as we went on. So I think this is starting to become more clear. And let me say, you are going to have lots of practice with null and alternative hypotheses as we work through various hypothesis tests in the next couple of weeks. But what I want to do for the rest of today is actually look at the logic of hypothesis testing that we're going to be applying to every single inferential test that we do throughout the rest of this semester and into next semester in Psych 204. So in the logic of hypothesis testing, we start by stating our null and alternative hypotheses, these two complementary hypotheses, one of which must be true. So here's the example I'm going to use. My null hypothesis is that people wash their hands at least as frequently as they claim. My alternative hypothesis is that people wash their hands less frequently than they claim. Okay, one of those two things has to be true. Now, here's the new part. What we're going to do is we're going to predict what the data should look like, assuming the null hypothesis is true. So if the null hypothesis is true and we go out and we collect some data, what should those data look like? So in the tea example, when they went out and they collected the data, they had Muriel Bristol sip those teas. If the null hypothesis was true, she should have been at random chance on guessing each of those cups of tea. She probably would have gotten about 4 out of 8 correct, because 50-50 chance on each one. That's what the null hypothesis would predict. Now for this example, 95% of people claim to wash their hands. That's what the data tells us. So if my null hypothesis is true and people do actually wash their hands at least as frequently as they claim, and I go out and I observe 200 people, then at least 190 of them should wash their hands, whereas only 10 of them should not wash their hands. If my null hypothesis is true, and that's the place I'm starting from. My null hypothesis is true. So if I observe 200 people, at least 190 should wash their hands. Everyone with me so far? You can probably see where I'm going with this. Okay, so now I'm going to obtain a representative sample from my population and collect some data. I'm actually going to go collect my data. And so in this example, I am going to go out and observe 200 people in a public restroom. Doesn't that sound like fun? And I'm going to determine whether they actually wash their hands before they leave the room. So I'm going to collect my observational data. Now, here's what we do when we look at these data. We are going to compare the sample data, what we actually observed, with the predictions that are made by my null hypothesis. And we're going to determine what is the probability of seeing the data I'm seeing if my null hypothesis is true. If there's a reasonably high probability, usually at least 5%, that the sample data could have occurred by chance through sampling error. Yeah, those data, that could have happened even if there's nothing going on. I retain my null hypothesis. That doesn't mean I've proven it true, but I retain it as a possibility. There's nothing going on here. People really do maybe wash their hands as often as they say they do. I retain my null hypothesis. I conclude then that there is not a statistically significant effect. When I say that there's a statistically significant effect, that's a phrase you're going to see in the literature over and over. What I mean is that there is enough evidence to reject my null hypothesis. Now here, if I'm not seeing data that are unlikely to occur by chance, I don't have a statistically significant effect. I'm concluding that I do not have enough evidence that there's something going on. I don't have enough evidence to say my null hypothesis is wrong. I have to retain my skepticism. Now, on the other hand, maybe there's a low probability, and usually we're looking for less than 5%. If there is a low probability that the data I'm seeing could have occurred through sampling error, simply by chance, like Muriel guessing all 8 cups of tea correct, really low chance of that happening if there's really nothing going on. In that case, I'm going to reject my null hypothesis. It is really unlikely that that null hypothesis is true. Less than 5% chance of seeing these data. Yeah, so that's probably not true. In that case, I conclude that there is a statistically significant effect. I have enough evidence to say that there is something interesting going on here. I'm concluding that my alternative hypothesis must then be true. There's a really low chance of seeing these data if my null hypothesis is true, so I reject that. And if the null hypothesis is false, then the alternative hypothesis must be true. So I now have data supporting this alternative. So back to our example. I want to compare my sample data with the null hypothesis predictions. So our null hypothesis predicted that 190 people would wash their hands at least, and 10 don't wash. Now let's say I go out and I observe, and I'm going to give you numbers that are pretty consistent with reality. 142 do wash their hands, 58 don't wash their hands. Now, let me say, this is consistent with pre-COVID reality. Hopefully, it's a little bit better now. Now, let me tell you, I'm not going to teach you how to run the statistics on this today, but if I ran statistics, I would see that there is less than a 0.001% chance of seeing these data if the null hypothesis is true. If at least 95% of people wash their hands, there is less than a 0.001% chance of observing only 142 of 200 wash. That is an extraordinarily low probability. So under these conditions, I reject my null hypothesis and conclude that my alternative hypothesis is correct. People wash their hands less than they claim they do. That is how hypothesis testing works. We start from this place of skepticism, this null hypothesis saying, yeah, nothing going on here. We use that null hypothesis to predict what our data should look like. We go out and we collect the data, and then we calculate the probability of seeing these data if the null hypothesis is true. If those data are unlikely to occur, there's a low probability of those data occurring. If the null hypothesis is true, we say, nope, that null hypothesis is almost certainly not true. So we look at our alternative hypothesis as the correct explanation for what we are seeing. There's one question. Oh, I have to show you this. I am convinced that there is a Far Side cartoon for every occasion. And this is just my favorite example of that being true. But here's what I was trying to leave you with. A thought question. And I'm not going to ask you in this moment, but we will come back to this next day. Why do we test the null hypothesis. Think on that, and we will have that as our opening question for next class. Have a great couple of days, and I'll see everybody on Wednesday.